Okay, thanks for coming even the second time. I'm happy that those of you who are here were not disappointed the other time. So what I will talk about today is a continuation of the lectures in cosmology, the general introduction into cosmology. I will first briefly summarize the previous lecture, and at least I will try to do it briefly, but there's the risk that I will do it at length. And then the topic of today is the cosmic microwave background. And the main way to interpret the cosmic microwave background as a source of information about the contents of the universe is by looking at its correlation function, looking at its spectrum of anisotropies. Then I will try to explain in the most simple way possible how you can compute the spectrum of correlations in a given model of cosmology. So I will try to show you what are the ingredients that go into the anisotropy map of the cosmic microwave background. I will briefly talk about a number of secondary anisotropies. I will explain what the difference between secondary and primary means in the cosmic microwave background. And then I will, in one slide, show the cosmological parameters from the cosmic microwave background, but it's actually something I've shown in previous lectures already. And that is the experimental constraint. So these 2 points are actually 1 point. So where did we stop last time? The most important message I tried to convey is that cosmologists observe light, which has an intensity and a wavelength and a direction, only 2 angles. So in terms of space-time, we only have 2 dimensions, 2 angles. Everything else that we try to infer about the 4-dimensional space-time of the universe comes from trying to add the other 2 dimensions using the information that is in the intensity and the wavelength of the light that we receive. But the important thing to keep in mind, I emphasized the other lecture, is that we don't see the 3rd dimension in space, and we don't see the time dimension in cosmology. We infer it. So 2 out of 4 dimensions. What I didn't explain very clearly the other lecture is the idea of the light cone, and I do want to show it in front of you because it has a crucial importance in cosmology, these 4 dimensions. So, what do I mean? We are an observer sitting here at a constant time and at a constant position, because at the scales of the universe we cannot move around at distances that are relevant for the size of the universe. Even if we travel to Mars, which takes years, this means nothing for the size of the universe. And also, the time that we have for our observations, maybe several human lifetimes in a row if generations cooperate together, that is really no time duration compared to the age of the universe. So we have we sit at a fixed point in space-time. We can observe in different directions, and light that we see has traveled a distance that is always given by r equal to the speed of light times the time that it's been traveling. So we only observe events from this line, and we observe everything at the same time. So for the space-time in this one-dimensional space, so this 1 plus 1 dimensional space-time, one space dimension, one time dimension. If you draw your 2D space-time in a plane with the time dimension on the vertical axis and the space dimension on the horizontal axis, your entire space-time is given by a plane, but all our observations really only come on these lines of r equal to ct. So this is an illustration of how cosmologists are constrained in trying to map the universe and trying to measure what is in the universe. We only observe a slice of the bigger space-time. And we have no idea what happens on the parts that we don't observe. We don't know what happens inside our light cone, although it may be causally accessible to us, but things that are even outside our light cone are completely unknown and really not accessible to us in terms of information. Although if you could wait for the age of the universe, we will move forward in time, and our light cone will be moving with us and will be spanning this line in space-time. So our light cone will, in later times, sweep out the rest of space-time. But we can observe only at one point in time, so we only have one light cone. the way we try to infer how far a photon has traveled along this line on which we do our observations is by looking at the redshift of the photon. And that is literally the ratio of the wavelength of the photon at which we observe it by the wavelength of the photon at which it was emitted. And given the Doppler effect, this redshift can be caused by a difference in velocity between the observer and the emitter. And if you picture the universe as everything moving away from us as expansion, the difference between velocity here and velocity there is related to the size of the coordinates and the change of the size of the coordinates. So redshift is directly related to the size of the universe. The photon stretches along with the universe. And then here was the only slide with equations in the other lecture, trying just to emphasize that the distance measures that we have in cosmology, luminosity and angular diameter distance, are functions of redshift. And if you compute them in the model of the universe that we use, then these distances as a function of redshift, so the distance to a point with a given redshift and to the other point with another redshift, is directly given by an integral over the expansion rate, which itself is a function of the matter content, the radiation content, the curvature of spacetime, and one part that fell off the slide, the dark energy content of the universe. So if you know the distances to different redshifts, you're actually measuring the expansion rate of the universe because that's what's in this integral, and you're actually sensitive to the matter content of the universe. So the angular diameter distance is a function of redshift, or actually the scale factor, because the redshift and the scale factor are related in a homogeneous universe. And the expansion rate, which is in this integral, then tells you what the distance is to a certain point. One point I also briefly touched on is that the cosmic microwave background is a very remote light emitter at a very large redshift. So the photons that we observe from the CMB have stretched by a factor 1100 roughly. And then and we see a particular angular scale in the CMB, and I'll try to explain in this lecture what this angular scale comes from. And that means that the CMB serves as a distance measure. So if you have redshift on the horizontal axis, this figure goes from 0 to 2, and you observe distances on the vertical axis, then the cosmic microwave background is a single but very well constrained data point at redshift 1100 on this figure. So it should be actually much farther out in this slide. And these are altogether the sources of information that we have about the universe, telling us what the expansion rate has been, what the matter content of the universe is. So that's in summary our light cone. And to put the previous picture of the nearby distance measures and the cosmic microwave background in this illustration, our observations are really on this line, on our light cone. We don't see what's inside, we don't see what's outside, we only see light that was emitted at such a distance and time that it reaches us exactly today. So something emitted 2 years ago must be at a distance of 2 light years away. That's a simple relation. Supernovae are nearby, cosmic microwave background is far away. That's a summary of the last lecture, and we have no information inside. And then you get to the conclusion already that the universe is filled with certain types of matter at different times. I didn't put labels on this figure because I made it while we were waiting for the last participants to enter in the lecture. There is redshift on the horizontal axis, and it's a logarithmic plot. On the vertical axis, there is the relative contribution of a certain energy component to the total energy budget of the universe. So radiation is in blue, and if you go to high redshifts, you see that radiation at this point was the dominant energy component in the universe. If you go to lower redshifts, so points more nearby, at a less stretched distance, you see that at some point dark matter, or actually all matter that behaves as dust, is at some point the most important component in the universe. And at very recent times, so redshifts below 1, dark energy is the dominating component in the universe. This is in the lambda CDM model, exactly. You can make it a little bit more general. It is in the homogeneous cosmology framework. Because if you assume that the universe is homogeneous, then you end up with this kind of matter content in the universe. Of course, you could put in other dark energy than the cosmological constant. So, but then it will still look pretty much like this. So the talk today will be mostly about this time in the universe. And that's why I put this slide in, to show you that the cosmic microwave background comes from redshift 1100. So radiation is the most important component in the universe. Matter is there, but it's really not so important. Dark energy, in the lambda CDM case, is not at all there. There are models of early dark energy in which the dark energy already at early times starts tracking the dominating energy components and only at late times becomes the dominating component itself. So it is present, but not the most important ingredient. These models exist. And the cosmological constant is really completely negligible at early times. So we'll be talking mostly about physics at this redshift. But the light that we see from the cosmic microwave background traveled from here to us at redshift 0 here. So it did travel through space-time in which dark energy played a role. And we'll see in one of the topics that this actually becomes an interesting part of the photon trajectory. So that was a summary of the previous. I hope that was fast enough. Now we'll talk about correlation functions, then perturbation theory, CMB lensing, and the parameter constraints. And this is it's a selection of things that you can do with the CMB. It's a selection of what I think is most important to show in an introduction on the cosmic microwave background. But there are other topics that I have no time to explain and that in other introductions of microwave background you might encounter. This is the cosmic microwave background as observed by the Planck satellite. Each of these rugby balls is a mole-weighted projection of the sky as we observe it, so the two angles of space-time to which we have access. And these maps of the sky are pictures at different wavelengths of the light. So this is the wavelength of the light, which I said is one of the pieces of information that comes from the light. And it varies from 30 gigahertz to 800 gigahertz, and you see that at different wavelengths, the sky actually looks quite different. The orientation of this projection is such that the galactic plane is the equator of this sky. And remember from the previous lecture that the ecliptic plane, which is the plane in which the Earth and the Sun are in the same plane, follows an S shape that goes pretty much like this in this orientation. The universe as seen by Planck. The cosmic microwave background is the cleanest black body radiation that we know from experiments. And it has the shape of a black body radiator with a temperature of 2.72 Kelvin. If that is your black body, then the peak of your spectrum, when you're measuring it in frequency, not in wavelength, and the peak is slightly different, is at 160 gigahertz. So that is the map that would be between this one and this one. That is the peak of the CMB map. But then why do you measure it at all these different wavelengths, and why does it look so different? Well, of course, there are different sources of radiation, and that is one of the complications in cosmology. You cannot simply say, well, this wavelength of light comes from this age of the universe, and this other wavelength comes from this other age of the universe. Because you see very clearly that the galactic plane is present in all of these maps of the cosmic microwave background. And it's aligned with the galaxy, so there is, it would be really strange if this signal is from outside of the galaxy and is actually from a redshift 1100. No, this signal comes from nearby. This is light at this wavelength that comes from the galaxy nearby, and this is not the cosmic microwave background that we want to study. So this very nicely illustrates that the cosmic microwave background is kind of polluted with foregrounds. You shouldn't call it pollution because it's everything that you see there is information. But it does make the game more difficult. And then you can combine these maps and try to clean it, and then you get to this cleaned map of the cosmic microwave background. And if you trust the people who did the analysis, then you can believe that this map is light that comes from redshift 1100. So a sphere around us at a very long time ago, at a very large distance, and light that was emitted when the universe became transparent. There's a question?
Yeah, out of curiosity, did you know why they didn't try to measure at 160 gigahertz, since this is the maximum of the black body radiation?
I think, I know I may be wrong, but my understanding of that is that you don't necessarily need to be at the peak to measure the signal, because you're interested in the anisotropies. And the reason that they chose 140 and not 160 is that you want to be at the frequency in which the foregrounds are least polluting. And if you look at the different sources of foregrounds, it turns out that actually 143 is the cleanest frequency in which you can observe the cosmic microwave background, even though it's not the peak of the Planckian spectrum. That's a very good question. Thanks. So after cleaning the map, this is what you end up with. And now let's start to do cosmology with this. We have a map with spots on it. Every spot is in a different direction. So what can this teach us about the fundamental physics that describes how the universe evolved at very early times? We try to do, well, if you have a model of the universe, or actually if you have a model of anything and you do measurements, you want to repeat the same experiment many times, because you know that there will be random contributions in it. And if you have a decent model of the thing that you're measuring, you'll actually know the distribution of the different values that you're going to measure. So when you know the distribution of the different things that you're going to measure, you should look at the power spectrum. And for a sphere, you do that in spherical harmonics. Let me try to make it more clear later. This wasn't very clear what I'm saying, but it should become clear later. If you have any map that's a function of two angles, you can expand it in spherical harmonics. That is just the same as taking a three-dimensional Cartesian spacetime and expanding your function in Fourier space. It's Fourier expansion on a sphere. The eigenfunctions are the spherical harmonics here, and the ALM are the coefficients. So, of course, ALM are then given by the inner product of your actual map with the YLM. This is very standard functional analysis. So you have your map, you can compute the different coefficients ALM. L is the angular momentum, and M is the different orientations that you can do with this angular momentum. I don't think I have a slide in which I make that more clear. But the angular scale, which is relevant for such a spherical harmonic, is given by L. So for example, L equals 1 is the dipole of your map. And a dipole is simply, if you take a sphere, it has a different value on one half than it has on the other half. That's a dipole. If you consider your three-dimensional sphere, your dipole can have three basis orientations: the x direction, the y direction, and the z direction. So if L is equal to 1, you're talking about the dipole. That's the spherical harmonic that describes the largest modulation on your sphere. You need 3 spherical harmonics to describe your total dipole, because you have 3 axes. So for L equal to 1, the value of M runs along the 3 axes. M goes from -1 to 0 to +1, from -L to +L. For the higher order momenta, you're looking at the higher order anisotropies on your sphere. Clearly you will need more, you can make more orientations with the same modulation on that angular scale. So for each L, which describes an angular scale, you have several coefficients ALM, namely 2L+1 coefficients. If you sum them all up, you get your power estimator, which in this notation we give the letter D. And I'll explain later perhaps why. So you have your map, pixels in different directions, you expand it in spherical harmonics, you sum over the m for each L, and then you get the power at each angular momentum L in your map. And this then perhaps tells you whether the map was random or was actually given by a correlated system. Then, okay, now I think I should be patient with the computer because it's just refusing to do its work. Right. You have your expansion of the map, and the sum of the two then gives you the D's. This is this D that I showed here, which is the sum over all m's, as a function of multiple moment L. This actual map leads to this actual spectrum. This is for each L the sum over all ALM for that L. And this gives you the power in different angular scales in the anisotropy map of the CMB. So this is not doing any correlations. This is just taking a map, expanding it in Fourier space, and looking at the amplitudes of the different Fourier modes, but then on a sphere. So if there's a peak somewhere, it means that the scale that that particular mode corresponds to has a very large amplitude, so it will be a very pronounced feature in your map. And you see a clear peak here, close to 1 degree, at L of about 200, I believe. And this tells you that there is a characteristic scale in the cosmic microwave background, and there's more peaks, and all of these correspond to different characteristic scales. So now it already becomes hard to believe that it's a coincidence that the map has this particular spectrum that is given by a random process, because there is an oscillatory feature in there. So this is already a hint that something must have happened. But I wanted to look at the correlations. Yes, now I see what's wrong. Sorry? Yeah, and I will explain why. Yeah. Now the question is if the CMB comes from where it's just a lucky thing and it happens to look the way it looks, or does it actually come from a correlated system? Is it set out by an underlying mechanism that tells you where the CMB should be hot and where it should be cold? Right? If I tell each spot on the sky to take a random temperature, it will not know about the other spots on the sky. So if I look at the correlation of the different dots, it will be uncorrelated. And if this process is not entirely random, I say I want you to be hot and you to be cold because you are at this and this distance apart, then the system is correlated. And we want to know if the system is correlated because then we can say whether these scales have any physical meaning. But it's important to remember the meaning of correlation. We're not really correlating anything in the cosmic microwave background. Correlation in statistics means an interdependence of variable quantities. I put this here to emphasize what correlation means. In an experiment in a laboratory, you can do 1,000 measurements of the same system in different realizations. And then you can actually sum up all these measurements and look at the correlations between the different measurements. But in cosmology, we have a problem. We only measure one universe, one realization. So fundamentally, it's impossible to measure the correlations in cosmological quantities. So what is the definition of two variables? What is the definition of a correlation of two variables? If I have variable A and a variable B, their correlation is defined as the average of their multiplication when I take an infinite number of measurements of this multiplication. This is the correlation of two variables. And if you design an experiment on Earth, you can actually do this. You can do a number of repetitions that is by all purposes infinite, and you can measure your correlation up to very high accuracy. If you wanted to do that with the cosmic microwave background temperature, correlate the temperature at spot 1 and spot 2, you would have to take the same sum. You would need to measure the temperature at spot 1 an infinite number of times, and the temperature at spot 2 an infinite number of times. But making sure that every time you measure it, you're measuring a new system. Then you can look at whether the temperature at spot 1 is correlated with spot 2. But for one human lifetime, the temperature in one spot on the cosmic microwave background is the temperature at a redshift of 1100. So it's a temperature in a direction of 2 angles, and at a distance r that corresponds to z1100, and a time t that corresponds to z1100, because it's on the light cone. It will always be the same remote spot in the universe that you're looking at. So if you measure it today and you measure it tomorrow, it will be the same temperature. It will be the same realization. So we are stuck at the first entry in this infinite sum that you would like to do if you want to measure correlations in the cosmic microwave background. So, no, we don't see correlations in the cosmic microwave background. We only see a spectrum of anisotropies. So, in many cosmology talks, you will hear that the cosmic microwave background here and there is correlated with each other, because if I see a cold spot there, there's a certain chance that there's a hot spot there. But this is actually a shortcut, because it's just one map. We didn't measure infinitely many CMB maps and correlate them with each other and measure the two-point correlation function. We only measure one map and take its spherical harmonics decomposition. Now, why can we relate this to correlations? This depends on a if statement. So I told you, you take the map, you transform it into spherical harmonics, you get the ALM coefficients given this equation, and if you sum out all the m's, you get this quantity as a function of a multiple moment L that gives you the power in L. How is that related to correlations? Now let's have a look. Let's imagine that we do have an infinite number of universes that we can measure. That we can repeat the cosmic microwave background observation with the Planck satellite in an infinite number of universes. And for each individual pixel, look at its temperature in this infinite number of realizations. Then we can tell something about the statistics that made the cosmic microwave background. If we could do that, we would take the sum to infinity of these measurements and correlate the temperature at two different spots. If you plug in the spherical harmonics decomposition of the same thing, of course these are just basis functions, it turns out that you're cross-correlating the different ALMs in your spherical harmonics space. Now here comes the if statement. If the cosmic microwave background is generated as a Gaussian random field, but only if, then the cross-correlation of your different ALM, so ALM with the complex conjugate of AL prime M prime, is given by CL, a constant as a function of L, times 2 Kronecker deltas. So this cross-correlator is only non-zero if L is equal to L prime and M is equal to M prime, and the value is given by CL. So it's a function of L only, not a function of M, and this shows you that this is a isotropic Gaussian random field because it does not depend on the orientation of my spherical harmonic, it only depends on the angular size of my spherical harmonic. So if the CMB is generated by a Gaussian random field, then we can with the actual value of this cross-correlator, which is CL times the two delta functions, we can work out the sum, so we lose the L prime and M prime sums, and we're left with a sum over M's only for YLM times YLM of two different angles, and this turns out to be a Legendre polynomial. So if the CMB is given by a Gaussian random field, then this cross-correlation of the temperature in different spots is given by these CLs. And these CLs are the correlation function of the cosmic microwave background. So back to the statement. For a Gaussian random field, that cross-correlation of ALMs is given by a function of L only, independent of M. So if you look at this initial quantity that I measured, the dL, which is a sum over M, this is actually a sum over many coefficients that are all drawn from the same distribution that has an amplitude CL. So if you look at large L, for example, multiple moment 1000, that means I have 2001 coefficients for that value of L. So I have A, 2001, and then the index M, 2001 of those. So the quantity D sub L then is actually a sum of 2001 independent numbers that are drawn from the same distribution with variance CL. So this looks very much like this cross correlator that I was talking about. And this is why these DLs are often called pseudo-CLs, because they do probe the original correlation function that describes how the CMB is measured. And here you have the answer to your question, Geneviève. Since DL is a pseudo measurement of the correlation function CL, it depends on 2L plus 1 coefficients. So if you go to small L's, large angular scales, this is a sum over only very few numbers. So you're sampling only very few coefficients of your distribution, which means that you have a very large error on your measurement. And for large L, large angular momentums, you have many measurements, so you get a smaller statistical error on your measurement of CL, because that is the quantity that we're after, the CLs, the power in a spherical harmonics momentum L. Large L, fair measurement of CL. Small L, you get a large deviation from the original CL. And there you go. So at small L's, you only have a few ALMs that enter in your sum of DL, because it's the sum of the ALMs. So you have a large error bar. And on the higher L's, you get a much, much smaller error bar because you have many coefficients in there. So fundamentally, all DL have cosmic variance with respect to the distribution function that we want to measure, because the distribution function is related to the fundamental physics that goes into the creation of the cosmic microwave background. And we want to know the fundamental physics that gives the background, because then we can measure the components that are part of the universe. We can measure the physics of the universe and test the physics of the universe. But all DL, the pseudo-CL, so the DL are the actually measured power in momentum L, have cosmic variance with respect to CL. Scales is the square root of L. So for the Planck satellite, which has a very accurate measurement of the cosmic microwave background, the instrumental noise is smaller than the cosmic variance on CL for all angular momenta lower than 1000. And everything above angular momentum 1000 is still limited by the noise of the instrument. So there you might actually be able to build a cosmic microwave background experiment that has a smaller instrumental noise than the Planck satellite. So there you may still improve on the cosmic microwave background measurements. And that is why, even though we have this magnificent instrument Planck, it is still important to use cosmic microwave background that comes, for example, from South Pole experiments, who only observe a small patch of the sky, not full sky, so you have different statistics, but they can build an instrument designed exactly for the small scale resolution, because remember, large L is small scales, it's like in Fourier space, and go lower than the instrumental noise of Planck and still get cosmological information. And I should have added one dot here, something to keep in mind. There is an important if statement. If it is a Gaussian random field, this line of reasoning is true. Because what we measure, this DL, is really just a transform of a picture. You have a picture, you transform it to spherical harmonics, and you look at the power of the different modes. That is not a correlation function. We don't fundamentally know if point A and point B are correlated with each other, because we would need 1000 measurements of them to get a fair estimate of the correlation. We really don't know. But if it is a Gaussian random field, then the observation of this one picture that we can do does give a fair measurement of the correlation.
Yeah, question? Just to make it clear, when you say that we don't measure the correlation, when you do a Fourier transform, actually the coefficient gives you the correlation, tells you how much the point here is correlating to a neighbor at such a distance. So it's still a spatial correlation between points that is encoding in the coefficients.
That is true. Yeah, you can formulate it that way. Let's see if we can make clear what the difference is between the two correlations that we're talking about. So you have the CMB map, all these spots that are hot and cold, and you could simply count how many are hot and how many are cold, and then you'll find that it's a very much Gaussian shape. And that's the distribution of your hot and cold spots. And in their spatial distribution, indeed, when you take the transform of the map, you will see that they're distributed according to certain angular scale. And that is indeed a correlation on your map. So, but what I'm trying to say is whether their origin between these 2 points, regardless of the rest of the map, is correlated. And that is the type of correlation that you would get from inflation. That is the type of correlation that we want to relate to inflation that I will talk about in 2 days from now. No, but it's a good point, and it's a pity that I don't have a better explanation of the difference between the two types of correlations, because they're obviously both correlations. But I hope at least so okay, I cannot make clear what the difference is, but I hope I made clear that what both definitions are.
I understand so what do we mean when we say so I think you explained it when we say that the CMB is generated on the Gaussian random field. It basically means what you pictured here. Yeah. That when if I drew how the temperature is really the distribution of the temperature, we'll see a Gaussian picked around on. Does it mean that actually that I would see a Gaussian picked on 2.72555 I don't know, in something that is a Gaussian variance?
No, that is this Gaussian. That is the points are all. This is centered at 2.7 Kelvin, and they're distributed Gaussianly around it. Now, the Gaussian random field I'm talking about is the density field from which the universe is created. Which means you have your density perturbations, delta rho, as a function of x. It is Fourier transform of its Fourier component. Now, this three-dimensional field is the density field of the universe. And if we could measure this, and even better if we could measure it at different times, so we add the time component here, then we would learn a lot about the universe. So that would be the ideal measurement if we had access to this. Now I need to jump ahead a little bit to inflation. If these perturbations are drawn randomly, that tells you something about the origin of the universe. If they're drawn completely random, not a Gaussian random field, so no correlations, but completely randomly, then the correlation between my delta rho at point x1 and t and delta rho at point x2 and t, this correlation, if it's an absolutely random field, would be 0. So actually, yeah, your question helps a lot, because even if I draw a random field of uncorrelated density perturbations, and I only have access to one of them because I'm a poor human that lives in one universe, this will have a value, and this will have a value, and their multiplication will have a value. But I cannot look at their correlator because I only know one of each value. So I still have a three-dimensional distribution of matter. I can take the Fourier transform of that, and I see that I get a correlation function in space. But I cannot say whether these density perturbations come from a process that creates correlated perturbations, or if they were just drawn randomly. Is that clear? And this is an interesting question, because this is exactly the question, where does the structure in the universe come from? And if you know where the structure in the universe comes from, you can say a lot about the space-time of the universe and learn a lot about fundamental physics. So if they're completely uncorrelated, this thing is 0, but one realization will give a Fourier transform with a certain power in it. And if it's a Gaussian random field that generated them, and I had access to infinitely many universes, I would find a number here. And the definition of a Gaussian random field is that this is not 0, but that this is in Fourier space given by d3k prime times their correlator delta k of time, of course, which I included delta k prime of time, and then this is a real valued quantity, so I can take the complex conjugate without any punishment, minus I kx1 plus I k prime x2. If it's a Gaussian random, so if it's a random field without correlations, this correlator is 0. If it's a Gaussian random field, the definition is simply that delta k prime is given by some width of the Gaussian three-dimensional Dirac delta k minus k prime, and then a factor 2 pi to the third. This is simply the definition of a Gaussian random field. If it is a Gaussian random field, it will look like this. So you can fill this in and work it out. So, what was your question again?
Yeah, my question is, when you see this oscillatory, I have trouble to understand why. So we have an oscillatory pattern in the CEMs, and then we say that it should come from a Gaussian random field or something. There is names that I don't get, or there must be some. I mean, yeah.
Yeah. Right.
What gives this oscillatory pattern is obviously complicated physics, but couldn't we get those oscillatory patterns without saying that it's a random field, but it's something completely different that gives a random.
That gives this pattern. Yeah, that's possible. That's possible.
Coming from an oscillatory from a Gaussian random field and having complicated physics.
Yeah. I mean, it's a bit like saying that you can compare it a little bit to the following. You have a box full of letters, individual letters, for like what you use in the press. You throw it in the air, it falls on the ground, and suddenly it spells out the Einstein equations. To keep it for physics oriented. That's possible, right? But it's much more likely that Einstein actually stood up and wrote them down. So by the observation of the cosmic microwave background itself, you really cannot tell whether somebody threw up a box and the letters fell on the ground in the right shape, or if there's a fundamental reason behind it that gives this picture. From looking at the picture itself and taking its Fourier transform, you don't know it. But you can have one model that gives a random, that says nothing is correlated and it's all random. Then it's very difficult to get exactly this power spectrum. You have another model that says it's a Gaussian random field with correlations. That does give the right spectrum. And if that is the field, then you can do the sum and measure the power and say this was actually the amplitude of the correlations. Okay? But that's a good question, because it helps to make clear what I try to explain, the difference between the correlations. Shall we move on, or are there more questions?
No. So yeah, just to make it clear, so all the complicated physics appears in this P of K, which depends also, I mean, it should be like a P of L if I wanted to translate it.
Right, so actually, yeah, so I do this in Fourier space because I'm more used to it, and I think many are more used to it. This P of K is, for this computation, the holy ingredient that goes in at the beginning. And we'll talk about inflation later, which tells you what this thing should look like. And this is the density field. So this is a distribution of matter perturbations in 3 dimensions. And I told you that at one time the universe became transparent, and an observer sitting at the center of your coordinate system observes the photons that come from a sphere drawn in this 3-dimensional density perturbation field. So if I would sketch it in two dimensions, so 2 space dimensions, x and y, I have my density perturbations going around here, and I put the observer in the center, the observer sees the cosmic microwave background coming from a surface in, or a circle in this case, in my two-dimensional space-time. And if you follow the density on the surface, it follows a pattern that you can relate to this three-dimensional field. That's just mathematics. Okay? So there was actually a fundamental reason why I talk about the three-dimensional density perturbations, is because that is what gives rise to the image, the spherical image of the cosmic microwave background. So, this is the sketch of correlations and what the microwave background looks like if it's a Gaussian random field. Now there's more we can do because we can actually compute the magnitude of these CL in our theoretical model. And that's how you can test test your model against the observations, and that's why the Planck satellite and all the previous CMB experiments give us such a wealth of information about the universe. So let me try to explain some equations. The cosmic microwave background photons, they scattered for the last time at some point in space-time and then left on their journey towards us. The temperature of each photon is, you can of course split it in the average temperature and perturbations on it, that's why it's delta T over T. The temperature of each photon is given to a number of different contributions. First, we have the photon density at the point where the photon took off towards us. More photons means higher temperature of your Planck radiator. Second term is the velocity, the relative velocity of that part of the photon baryon plasma with respect to the observer. If it's moving away from us, the photon will be slightly more redshifted than when it's moving towards us, that small patch of the universe where the photon comes from. And then there's the third and most important term, that's the gravitational potential. The photon has to climb out of a gravitational potential, or it will fall off a gravitational potential hill and will then hence lose or gain energy. This is at last scattering, when the photon leaves its last point of the photon baryon plasma. Then it travels towards us, and the most important contribution to the photon temperature coming from the strip towards us is the value of the gravitational potential at different points of the photon path. But of course, given energy conservation, if a potential is constant, a photon falls in, comes out, and at the end of the road hasn't gained or lost any energy. But if the gravitational potential is not constant, the energy loss when climbing the initial hill is a different value than the energy gain when coming off the end of the hill, because in the meantime the potential changed. So CMB photons in this drawing here left from a certain density in the universe and then travel towards us, and while traveling towards us they cross all types of different potentials and gain or lose a little bit more energy. And then the question is, when we have our telescope here observing in all directions, what is the distribution of temperature perturbations that it sees? And let me try to go on with this perturbation. If perturbations are adiabatic, that means if the photons and the baryons and the dark matter are distributed in the same way, so there's an overdensity of all of them in the same spot, and there's an underdensity of all of them in the other spot. That's the definition of adiabatic perturbations. And it turns out, I will not go into the alternative, which it means that you also have entropy perturbations on top of that. These are, by observations, constrained not to be very large. So if perturbations are adiabatic, then it means that the density in my photon gas is directly related to the value of the gravitational potential. Because I have more photons, I have more matter overall, I have a deeper gravitational potential. If I have less photons, less matter overall, a less negative value of the gravitational potential. So the photons are directly related to the value of the gravitational potential. This term is negligible, the velocity term. So the net effect of this first term, the ordinary Sachs-Wolf effect, is a sum of minus 20/3 and plus 2, because this phi is actually equal to minus psi. I omitted to put that on the slide. So the total sum is that the temperature of a photon is equal to 1/3 times the gravitational potential. So now why did I take you to this dry equation and this sum for adiabatic perturbations? there's a very funny result of this. When you look at a hot spot, does it come from an overdensity or an underdensity? That's a question to you. Yes? Overdensity. Right, you would guess it's a hot spot, so there's more gas because it's hot, so the photon comes from an overdensity. But look at this term. The photon density is directly related to the gravitational potential. If I have more photons in the spot, it also means that the gravitational potential is deeper. And I have to take both effects into account. And this line tells you that the net effect is that gravity wins. So I have more photons, but also a deeper potential. And the depth of the potential turns out to be slightly more important than the overdensity of photons. If I have less photons elsewhere, the gravitational potential is higher. And that means that the gain of energy from the photon when it leaves that potential is higher than its initial lack of energy from coming from a photon underdensity. And that is all encoded in the sign of this equation. This is a positive sign. So this is a funny fact that I want you to keep in mind, because it does come back every time you look at CMB pictures. A hot spot is an underdensity, and a cold spot is an overdensity. Okay, this is a very simple fact that I hope you take home from looking at this slide. So gravity wins. Hot is underdense, cold is overdense. And the next step is computing the values and the distribution of these ingredients that go into the temperature of a photon. And I will try to get you through that very superficially as well. So let's see. The Einstein equations, I didn't put the Einstein equations here, I only give the result. Give this result. You start with the assumption that the universe is homogeneous, with on top of that a small perturbation. You can write down the metric for such a universe with such a perturbation. You put that in the Einstein equation, and then the result is the following. Phi is the perturbation in the metric, and that's the gravitational potential. And so is psi. And I already told you that for perfect fluids, I didn't say it's for perfect fluids, but it comes from the fact of perfect fluids that phi and psi are of opposite sign equal to each other. So phi minus psi is equal to 2 phi. So we have the gravitational potential on this side of the Einstein equation, and on the other side we have the energy perturbation that comes from the not component of the stress energy tensor. Rho is the average density, and capital D describes the density perturbation, just like in this equation. Capital D describes the density perturbation of the photons. So this is Poisson equation. That's all it is. But it comes from linearizing the Einstein equations. Poisson equation tells you a relation between the density perturbation and the gravitational potential. And this kappa here comes from spatial curvature, which I will not say much about. And there's a second equation for the velocity term and the pressure. So the average density and average pressure times their perturbation is given by this relation. This is one of the other parts of the Einstein equation. And then the third one relates the pressure to the gravitational potentials. I put that there in case somebody wants to know the details. But let me carry on, because this does lead to something that I can I hope I can give you a clear picture of. So we have the Einstein equations, and on top of that you have the energy conservation equations from the stress energy tensor. I hope that is standard physics to you, which basically is the equation of motion of the photon gas. So I have these equations relating my matter perturbations to the gravitational potentials, and I have these equations giving the time dependence of the photon gas and the pressure perturbations. And next we there's a mistake there. Okay, next we put these equations, we simplify these equations and throw away the terms that you don't get if you only have a radiation fluid. So I get that the time derivative of my photon fluid is given by the velocity perturbation, its time derivative is given by the potential and the density perturbation. So you see that you can work these out. So what do you get if you put this result in here? You see that you get simply a second order differential equation. So that's always an oscillating solution. And this is quite intuitive. I have a photon fluid with density perturbations. So of course, since there's a pressure, I will get an oscillatory solution. Okay? I hope you already get where this is going, because I mentioned oscillations now, and I mentioned oscillations much earlier when we looked at the CMB correlations. So the solution to this is some oscillatory function, where this x is the Fourier mode k times a time parameter eta, and eta is simply it's a straightforward function of time t. So when eta grows, it's because t grows. So why is this function, why is this parameter x interesting? Why does it depend on k and eta? It tells you that different length scales follow the same oscillatory pattern, but at different times. Okay? And then, of course, the gravitational potential is related to the photon perturbations from what we saw before. So this is simply the Boltzmann equations at work in general relativity for a photon fluid with a pressure in the early universe. You get an oscillatory solution on small scales. I say small scales because things can only oscillate if there's a causal contact between the two different parts. If they don't know about each other, they're just pretending they're a homogeneous universe. So the equation for x much less than 1, that's saying for very small k, or for large k but at very early times, that is as much as saying for the cosmologists in the room on super Hubble scales. The equation on the previous slide gives a constant solution to the gravitational potential. For large x, so for very large k, or anyway for very late times, so on sub-Hubble scales, you get the oscillatory solution. And then we take a shortcut, compute the CL spectrum that comes from that fluid that has that distribution, and you get exactly this. So in red we have the data points as measured by the Planck satellite. Beware though that these are actually discrete points on the x-axis, it's multiple moments. So actually I should have a single data point for each tick on the x-axis, and this presentation is binned in the x-axis, but that's only for presentational purposes. When you do the actual fit, you do it with the unbinned data. But because of the binning, you get nice small error bars, and everything is very much centered on the best fit model. The green line is the best fit lambda CDM prediction for the cosmic microwave background spectrum. So the green line is the CLs, because we did a computation of the distribution of perturbations in the universe, the expectation of the distribution of photon perturbations. That's the CL, the actual width of my Gaussian random field. The red dots are the DLs, the pseudo CLs, which is the power in my multiple moment L as seen in the spherical harmonics transform of the CMB map. So the green line is the prediction of a Gaussian random field, a correlated system, and the red dots are the transform of a picture. That don't tell you whether 2 points are fundamentally correlated because we don't have an infinite number of measurements. But it does tell you what the typical length scale is in the perturbations in that map. And if the field is Gaussian, this DL does probe many ALM for high L's, and therefore does probe what the fundamental CL that goes in there was. And that's why you get these big error bars, because DL is not the same as CL. So the measurement of the power is not exactly the same as the correlator that the theory predicts. That's why you have this difference between theory and observation. And this green band around the line is the actual prediction of the cosmic variance from the theory. And the red error bars are a sum of measurement error and cosmic variance. Okay, so I hope that in the previous 2 slides I explained very roughly how the perturbation theory works that goes in the cosmic microwave background. And I hope I convinced you thereby that we can compute, by putting in more or less photons, what these oscillations will look like. Right, I would have liked to put in one more slide, which I forgot to put in, and that is to explain what these peaks really mean. But maybe, okay, I get a chance to do that later. So anyway, they really come from the oscillations in the baryon photon plasma. Okay, so they're true oscillations of a field. If it is a Gaussian random field, because the observation is just one picture, one measurement, and you need to keep in mind that you're depending on that if statement. Okay, let me carry on and briefly summarize other effects that go into the CMB that I did not explain. I only focused on the most fundamental ingredient, that is the photon baryon plasma that leads to the oscillations. But the photons, as I already sketched in that tiny cartoon there, travel through the universe towards us. And one effect that the photons get is that they get lensed a little bit. If they travel past a very large cluster, you can imagine that the photon path deviates a little bit. Photon path. So if we look in a direction n, it's just phi and theta, we observe a certain temperature. But the temperature that we observe there is from a photon whose path was lensed. So if we want to project it to the actual map at redshift 1100, we need to take into account that the photon actually comes from a slightly different direction, n prime, which is given by the sum of the direction in which we're looking and the amount of deviation of the path of the photon. Now, if you know the distribution of matter, or you predict the distribution of matter, you can predict what this effect is. And a very good review is by Lewis and Challoner, from which I took this figure. And in this figure you see illustrated the spectrum, and this time it's in a log scale, so that's why it is slightly skewed with respect to the previous pictures. The spectrum of temperature perturbations follows these nice oscillatory features, but at the very small angular scale, so the very large multiple momenta, you see that the lensing contribution to the anisotropy spectrum starts dominating the primordial temperature perturbation. This lensing is an effect on the photons in the late universe. So if I can quickly jump back to the slide in which I showed the matter content. The photons are emitted here, and they travel to us. So everything that happens in the universe between last scattering and here affects the lensing of the photons. So even though I've so far been talking only about physics happening at this moment in time, the spectrum that we observe is affected by the ingredients of the late-time universe. So, going back to where we were, I should have, right, that's where we are. What was I saying? The photon spectrum is affected by dark energy. And nowadays we have access to very accurate CMB measurements at these scales. They don't come from the Planck satellite, but they come from, it's ACT satellite, the Akatama Cosmology telescope, or CMB telescope, I forgot, I'm just guessing now. But they were I think I have the right experiment in mind. I think they were the first to actually fit CMB data only and get a detection of dark energy. So CMB is very early universe physics. Fortunately, it is all linear perturbation theory, so mathematically we can do it very rigorously and make no error. And it's a very clean signal, and already with that signal, we cannot fit the data without including dark energy. And eventually, this type of measurement should also give access to the masses of neutrinos, because they also play a role in large-scale structure, which I will try to explain tomorrow. So that's for the CMB lensing. Another secondary anisotropy that I want to briefly explain is the reionization of the universe. So the photons decouple at redshift 1100, and they decouple when the temperature of the baryon plasma, photon baryon plasma, has dropped so low that electrons and protons can form bound states, hydrogen atoms. So if the temperature is too high, they will, even if they bind, they will scatter again and will lose their bound state. The temperature has dropped so low that they form the bound state, which means that every electron finds its proton. It's very romantic, and they stay together for giga years until a redshift of roughly 6, when stars start forming and a lot of new high energy radiation is emitted into space-time, and the free hydrogen atoms are ionized again. The electron is split from its positron. It's a dramatic story, actually. When the universe is ionized again, it's full of charge. So photons, as you know better than me, will then experience some effects from this charge that is there in the universe. Photons will be rescattered by the reionized universe, and that means that CMB photons are redirected in new directions. So the CMB photons from different directions are mixed. This causes a smoothing of the anisotropy, and there's a very nice illustration by Wayne Hu. I took this slide from one of his presentations. This is a two-dimensional illustration of the universe, very much like the picture I drew there. The observer sits in the middle. The observer sees the CMB in different directions. The fundamental surface of last scattering is this big outer ring. The photons last scattered and went on their journey towards us. The black part is the age of the universe in which the universe was neutral, not ionized. The transition from black to white is the point and redshift, and here is the zoom in. So the radial distance is at the same time a time distance. I hope that was clear. The transition from black to white is the point where the universe starts becoming ionized again. So suddenly, from this black point, from this transition on through the white space, the universe is ionized, and at this transition, when you live here, the CMB is given by this ring because the universe is much younger. You see the CMB in different directions, and you can scatter the CMB photons into new directions. So let me try to repeat that. The radial direction is time. So when we look at a large radius, this is the very early universe. Last scattering was very recent. So at any point, I know the distance to the last scattering surface, but the last scattering surface is also at a same distance in the other direction, schematically. So when I sit here at this time, this is my cosmic microwave background. I will scatter cosmic microwave background photons in all directions. That means that I will scatter all these photons also in this direction. So what we observe sitting here is not a clean signal of this ring, but it's an admixture of cosmic microwave, it's an admixture of the original ring plus cosmic microwave photons from the other directions. That is the effect of reionization, and I hope you can imagine that this smooths out part of the anisotropy because it makes a mix of many colors. Another secondary anisotropy that I need to warn you about is the Sunyaev-Zel'dovich effect, which tells you that photons rescatter of the gas, of hot gas, in galaxies and clusters of galaxies. These are objects between us and the surface of last scattering. So in this picture, galaxies are living everywhere, they're filled with gas, and the photons can rescatter of those as well. This produces spots in the CMB. Now, if you can resolve the actual cluster with an astrophysics experiment and the cosmic microwave background behind it, and you can relate the cluster to the spot in that direction of the microwave background, that's good news, because you can remove it from your microwave background analysis. That's one thing. So you can remove signal that is not primordial, and you can keep a cleaner cosmic microwave background signal. And at the same time, by relating the temperature of the CMB spot and that cluster, you may be able to tell something about the mass of that cluster. So you hit two birds with one stone. You may get a cleaner map, and you get information about the clusters in the universe, which is again a source of information for the structure of the universe, for the space-time of the universe, and for cosmology. However, if you don't resolve that source, you know that there are spots in the CMB that don't come from the primordial spectrum, and that's a source of anisotropy that you don't want to include in your analysis of parameters.
I was told that actually they see very clearly in Planck, they see very clearly the Sunyaev-Zeldovich effect.
Yep.
And they can remove it.
Yeah.
I'm not sure. I'm not sure that they need really the cluster to be resolved to remove the effect from the overall picture, because they have so many channels.
Oh, that's true. That's true. Yeah, that's true. Because of course the cluster produces a spot with a different temperature and a different spectrum than the cosmic microwave background, because it's no longer a black body spectrum. Yeah. So that way, by combining the different wavelengths, you can try to remove many of those. That is true. Yeah. Yeah. Thanks. Okay. Now I've explained the main ingredients that go into the cosmic microwave background computation, and now I want to show you in the last few slides the only thing you should really care about, and that is, how does the CMB help us to understand the universe, and how does the spectrum change if we have different ingredients in the universe? And here we get to the point that I also mentioned earlier, trying to explain to you what the different peaks mean. So let's first focus on baryons. What do these different peaks mean for the baryons? Let me try to illustrate that. I have hopefully convinced you that the photon baryon plasma is oscillating. But I didn't say anything about dark matter. So let me try to briefly explain that. Dark matter has no pressure, at least not on the scales of the cosmic microwave background. So the dark matter just has a density perturbation, and it is probably collapsing. So if it's density on the vertical axis and distance on the horizontal axis, this is a low density. Let's do it different. Let's put the gravitational potential on the vertical axis. The gravitational potential here, so we have high density, deep in the gravitational potential, low density, very high up in the gravitational potential. The dark matter has no pressure, so it simply is collapsing. It's moving towards the center. But it's slowly, but without pressure. Now, on top of that, I have a photon baryon plasma. And most of the mass in that comes from the most density comes from photons. So I have my photons that want to fall in, but here I have pressure from my photon gas. So I will produce, at first time, an overdensity. Pressure is pushing outwards, so it will be relaxing again. And I will reach the maximum of my oscillation, in which this is actually in terms of photons. So the dark matter doesn't move, the dark matter stays where it is. But that the photons actually here are relatively underdense compared to here. So let me draw the same oscillation twice. This is the dark matter. At one time, I have many photons here, and only very few here. The oscillation, the pressure pushes it out, so at a later time I will have very few photons here, but I will have many more here. Now, what are the different peaks in the CMB? The different peaks measure power. So this is related to the absolute value squared of the actual temperatures. So the first peak is at the very large scales. The first peak is from density perturbations that have just reached their first maximal overdensity. So the photons are all together in the bottom of the potential at a high density. Exactly, so maximum isotropy. There's a high density here, makes very cold photons, remember that? And there's a very low density here, makes very hot photons. So I have the maximum anisotropy. I'm at the maximum of my oscillation. Very cold spots, very hot spots, at large scales. If you focus on a perturbation at smaller scales, then the photon plasma on those scales has already been at a first maximum overdensity and relaxed to its maximum, so to say, anti-correlated density spectrum. So I have an overdensity of photons here and an underdensity of photons there. That is the second peak. So the second peak is actually a peak of a perturbation in my photon baryon plasma, where I have an overdensity of photons on top of a small underdensity in my cold dark matter. And then the third peak is a perturbation that has already had a contraction, expansion, and contraction again, etc. And that's why the spectrum of peaks goes on until the smallest scales that we can access. Now what happens if I add more baryons? If I add more baryons, then the gravitational pull towards this first oscillation is large, and my maximum expansion will be slightly less efficient because I have too much mass to move around. So if I add more baryons, those perturbations that are in the anti phase of their oscillation will be slightly less pronounced because it's slightly less efficient because of all the mass in the baryons. So if you add baryons to this picture, what you see is that the odd peaks become more pronounced and the even peaks become less pronounced. Okay, the odd peaks, so 1, 3, 5, etc., are the peaks that are at their contraction for the oscillation. So I have my overdensity of photons and baryons at the positions of the overdensities of my cold dark matter. The even peaks are in the opposite phase. I have my overdensities of photons and baryons in the underdensities of cold dark matter. And that's why adding baryons makes a clear change in the relation of the odd to even peaks. And this is why the CMB gives such a very, very tight constraint on the relative amount of baryons in the universe. The next is dark matter. It roughly gives the opposite effect because if you change the amount of dark matter while keeping the amount of baryons constant, you make this initial wave that is there more smoothed out because you simply have less dark matter to perturb things around with. So the CMB is very sensitive to both dark matter and baryons, and the reason is that dark matter has no pressure, so it does not take part in these oscillations in the photon baryon plasma. So from cosmic microwave background physics alone, you already need very large abundance of dark matter relative to baryons. And this is why even in cosmology, with the cosmic microwave background, there's very convincing falsification of the absence of dark matter. That's the clearest way to say it. You need dark matter in the cosmic background. Okay. Then reionization, which I tried to explain in one slide, in the two previous slides. It causes a damping of the peaks because you're mixing photons from different directions. So it's like you take a beautiful painting and you start mixing around the colors. So if you increase the amount of reionization, you decrease the total power in your temperature anisotropies. Now I get back, I can make a connection to the previous lecture. We observe very clear peaks in the cosmic microwave background at an angle. That's really an observation. We observe radiation in different directions. Given the model, we can compute the original length scale in the photon baryon plasma. That corresponds to the largest peak on the largest scales. If you start with a hot Big Bang, so the initial situation, and you wait for 300,000 years, then you cool down sufficiently much to the temperature where the photons decouple. Clearly, any piece of information can have traveled at most 300,000 light years. And that is why the first peak of the CMB is at a length scale that is roughly 300,000 light years separated. This is not entirely true because I'm mixing co-moving and physical scales. It actually corresponds to 300,000 light years in the universe today. So you need to divide it by 1100 to get the actual physical scale of the first peak there. But if you forget about the expansion, it is very simple. The first peak of the CMB is at a distance of 100 megaparsecs. That is, oh sorry, I said 300,000 light years, but here of course I give a factor of 1,000 more. So that is the expansion taken into account. The co-moving length scale, so the distance between a hot and a cold spot, that is from the first peak in the cosmic microwave background, that distance today, taking into account the expansion of the universe, is 300 million light years apart. That distance at the time of last scattering, so that's a factor 1,000 smaller universe, is 300,000 light years apart. So the first peak is a length scale which we know. We observe it at an angle, we know its original physical scale. If you know how big something is and you see the angle, you can compute how far it is. And this is why the cosmic microwave background is also a very good measurement of the angular diameter distance to redshift 1,000. And I explained to you how the distance measure is related to the age of the universe. So, to the expansion rate of the universe, and the expansion rate of the universe is again related to the age of the universe. And that is why, given the CMB, we can get a very strict bound on the content of the universe, on the expansion rate of the universe, and on the age of the universe. That's written there. The expansion rate is actually very much degenerate with the curvature of the universe and the dark energy content of the universe. I don't think I will explain why, but the motion of the peaks when you... unfortunately, I cannot pause this movie, or can I? I can. Let's abuse this picture a little bit. Okay. You see, by changing the content of the universe, or the expansion rate of the universe, which is very much related, I simply change the angular position of the peaks. And since these peaks are at a scale of 1 degree roughly, we get to the conclusion that the universe has the age it has that we conclude today, which is 13.8 billion years. And in this movie, of course, you can see that the CMB is also sensitive. Well, I didn't clearly explain why, but it's very sensitive to the spatial curvature of the universe and to the dark energy content of the universe. So, actually, the best constraint on omega lambda from the CMB comes from scales that are invisible in this plot. It's from the CMB lensing that I showed earlier, that goes to multiple moments of the order of 10,000. But you don't see it so clearly here because of the way of plotting, simply. So that is it. That is how you can use the cosmic microwave background, particularly from the Planck satellite, to constrain cosmology. You have a picture of the sky, you take the Fourier transform, you assume that it's given by a Gaussian random field, so you can relate this to the statistics that generated the universe. If you know the statistics, you know the typical length scales, then you know the distribution of your density perturbations, and you get to this picture, which I already showed in the previous lecture. But this is the result, the main result from the cosmic microwave background. I added one parameter that is not in this slice, and that is the expansion rate of the universe today. Now with Planck, with just the CMB, you need dark energy because the CMB lensing is observed. Actually, it's also observed in Planck itself. I didn't explain how, but it is. You need dark energy, dark matter, baryons, photons, and neutrinos, and an expansion rate that is this value. I forgot to put a unit. This is in kilometers per second per megaparsec. And this is the big conclusion of the lecture today. This is what the universe looks like if you assume that the CMB is a Gaussian random field. Thank you. Any questions? Many questions. Yeah?
Is there any observational arguments to say that we have a Gaussian random field?
Yes. Yes, there are observational arguments. Let's see how it's there. Well, it goes in different directions. One is the basic question of, are these temperature perturbations themselves Gaussianly distributed? If you forget about that direction, but you just put them all together on one pile and you count what they're distributed like, is that an exact Gaussian shape or not? And that is a very hot topic of research in cosmology. So I plotted this, it's just a Gaussian, of course, the distribution earlier. So this is delta t over t, and this is their fraction relatively. the question is this an exact Gaussian shape or is there a small deviation from it? And it might be slightly non-Gaussian. And of course, saying non-Gaussian is saying it's anything. So this is there are a lot of possibilities. So in order to decently analyze this type of non-Gaussianity, you actually, in theory, need to go through all possible functions that you can imagine that describe a shape. But for the most typical shapes of non-Gaussianity, and the most typical then means the most typical ones that inflation can give us, the CMB spectrum is currently constrained to be Gaussian at 1 part in a lot. And let's say this is Gaussian up to, I think, 1 in 10 to the 10th. No, it's not the order 1. So let's say it's of the order of 10 to 10 to the 10th. But that's just the distribution of the spots. Now, whether the original generation of the CMB is in a Gaussian correlated field is observationally difficult to probe because we just have one field, but the theory that predicts that it should be a correlated field makes other predictions that you can test as well, and one of them is this B-mode lensing that the BICEP satellite perhaps detected. I will try to explain that in the inflation lecture. If there is no other model that explains such a correlation, and inflation does predict such a correlation and it is observed, that is a very strong hint that the system that generated the perturbations actually did generate Gaussian random field. But it will all be indirect evidence.